In this video, we're going to talk about part 2 of experiment 2, which is the section we're going to focus on. So I just want to remind you the sections of a pre-lab. So we need the title, the objective, the hypothesis, the variables, the experimental outline, the chemical hazards and waste, and the key math equations. Before we talk about each of these for this experiment, I want to talk a little bit about what we're doing in this experiment. So the first thing we're going to do is we're going to make a series of saltwater solutions. We're going to make 5, 4, 3, 2, and 1% saltwater solutions by mass. We're then going to take those saltwater solutions and we're going to measure the conductivity of each. We're going to use those values of concentration and conductivity to generate what's called the calibration curve. A calibration curve relates data that we can relatively easily measure, in this case conductivity, to data that we cannot easily measure, in this case concentration. We're then going to use that calibration curve and the conductivity of a saltwater solution to determine the concentration of salt in the unknown seawater solution. So the title of this experiment could be something along the lines of determining the concentration of salt in an unknown seawater solution, or what is the concentration of salt in an unknown seawater solution, something like that. The objective is to determine the concentration of salt in the unknown seawater solution. For the hypothesis, we want to go ahead and use the lab manual. So if we go to page 38 of the lab manual, we could find this information about the hypothesis. It says sentence 1 should contain a specific prediction of the amount of salt, sodium chloride, in the seawater sample. If you Google how much salt is in seawater, you may find that it's about 3 to 3.5% salt. So you could use that for your prediction. The second sentence should contain the following: a calibration curve. What is a calibration curve? What should be on the x and the y-axis? In our case, on the x-axis, we're going to have the concentration of salt in mass percent, 5, 4, 3, 2, and 1%. And on the y-axis, we're going to have the conductivity, and the conductivity is in microsiemens per centimeter. And the purpose of the calibration curve is to relate something that we can easily measure, conductivity, to something that we want to know, concentration. In this case, we want to know the concentration of salt in seawater. The third sentence should contain the following: the type of proportionality between conductivity and concentration. These things are directly proportional. As we increase the concentration of salt, so too does the conductivity increase, because there are more ions in solution, which allows more current to pass through the solution, which also answers point E here. Why is there a relationship between concentration of ionic compound and conductivity? So this is how we're going to find our hypothesis. Next, we need to do the variables. So in this case, our independent variable, or our experimentally controlled variable, is the concentration of the solutions. Again, we're going to make a 5, 4, 3, 2, and 1% solution. Our dependent variable is the conductivity. The variable we're going to measure is the conductivity of each of these solutions. The experimental outline, I'll discuss more here about how to make the solutions, how to measure the concentration of the solutions, and how to make the calibration curve, but you can use that information to determine the experimental outline. I would strongly suggest that you have enough information in your experimental outline to make your solutions without having to look at the lab manual. Said another way, you should have recipes for your solutions. Chemical hazards and waste. It's salt water. There's no real hazards here, but the waste can go down the drain because it's just salt water. And then finally, the key math equations. There are two key math equations here we're going to use: the dilution equation, C1V1 equals C2V2, and the mass percent equation. Mass percent equals the mass of the solute over the mass of the solution times 100. And in the next section, when I talk about making the solutions, we'll use both of those equations. So this is essentially what we're trying to accomplish in this experiment and how to write the pre-lab. So the next thing we need to do is actually to make our solutions. And what we're going to do is we're going to make solutions of different mass percentages. Mass percent is equal to mass of the solute, in this case salt, divided by the mass of the solution times 100. So the first thing we're going to do is we're going to take a container and we're going to tare it. And right here it tells us what to do is to add about 3.75 grams of salt to the flask. So we're not going to be able to add exactly 3.75 grams, but we're going to add approximately 3.75 grams of salt to the flask. We're then going to add about 71 milliliters of water. The density of water is 1 approximately, so 71 milliliters of water is going to be about 71 grams of water. That'll give us 3.75 plus 71, which is about 74.75 grams of solution. We can then calculate the mass percent of the solution, which should be around 5%, by taking the mass of the solute divided by the mass of the solution times 100. The problem is, you're not going to be able to do this perfectly. You're not going to be able to do exactly 3.75 grams of salt and exactly 75 grams of solution. If you did that, it'd be exactly 5%. So what we're going to do is, we're actually going to calculate what we made. And to do that, I'm going to show you how to use Excel. So in Excel, we have some actual numbers. Instead of 3.75, we added 3.9285 grams of salt. Note that we should have 4 decimal places for each of these. So in order to find the mass percent of this solution, we want to take the mass of the salt, then divide by the mass of the solution, and multiply by 100. This will give us the mass percent. Note that it's not exactly 5%. So we didn't use exactly 3.75 and we didn't have exactly 75 grams of solution. Don't worry about it. We don't need it to be exactly 5%. We need it to be approximately 5%. And we also need to know exactly what percentage we did have. You'll also notice that this value populates down here automatically because we want to use the actual concentration. Now what we need to do is we need to take this approximately 5% solution, which again we made by adding about 3.75 grams of this and about 70 of salt with about 71 milliliters of water, measuring the mass both times, and we want to turn it into a 4, 3, 2, and 1% solution. So how are we going to do that? To do this, we want to use what's called the dilution equation. And the dilution equation is C1V1 equals C2V2. And in order to do this dilution, what we need to do is we need to plug in our values. So our initial concentration is 5.2079%. That's what we just calculated. The initial amount of that, the V1 that we want, that's our variable X, or I'm just going to leave it as V1. The final concentration are 4, 3, 2, and 1. We have to do them one at a time. But in this case, I'm going to put 4.0%. Then finally, our final volume is 25 milliliters. So this is the final volume that we want to make because that's what the lab manual tells us. Multiply these two together and divide by this one, and you find that V1 equals 19.2, make that 4.00 milliliters. What this means is we take 19.2 milliliters of this solution and we make the total volume 25 milliliters. Said another way, we add 5.8 milliliters of water to this particular solution, 19.2 milliliters of it, and we'll have a 4% solution. We can then measure the conductivity of that solution. Remember, we're making the solutions and we're measuring the conductivity, and we're going to make a calibration curve between the concentration and the conductivity. So because making these solutions is repetitive, it's easier to do it in Excel to make these recipes. So in order to do this, we're going to use C1V1 equals C2V2. In this case, we want to take the concentration that we want and multiply it by 25. This is C2 and this is V2. We want to take that value and we want to divide by C1. In this case, this is our C1. Because I want to drag this down and find the recipe for the 4, the 3, the 2, and the 1% solutions, I don't want this A to drag. So I hit F4 and it puts dollar signs around it. So $sign A, $8 tells Excel don't drag that cell, only drag this cell. So this will become A10 when I drag it down, but this will stay as A8. So what this tells us is we need 19.2 milliliters in order to make this solution. We can then drag this down, and then we need 14.4, 9.6, 4.8. Excel's not so good with sig figs, don't worry about that. To find how much water we should add to this, remember that the total volume should be 25. So if we take 25 minus how much is the 5% solution, this will tell us the volume of water to add to each one. We now have a recipe, if we drag this down, to make all of our solutions. To make the 4%, we take 19.2 milliliters of this and we add 5.8 milliliters of water. Note that your recipes will be slightly different than my recipes because you're not going to make exactly a 5.2079% solution. you're going to make whichever solution you make. The next step is to physically make 25 milliliters of each of these solutions and measure their conductivity. The next section of the video will talk about measuring the conductivity. But one word of warning I would like to give you is, please make sure that you keep all of your solutions, because if you accidentally measure the same one twice, which is very common, okay, and you dumped it out, you obviously can't remeasure it. But if you still have the solution, you can measure it again. In order to measure the conductivity, we need to use a conductance probe. Begin by inserting the cord into the conductance port on the front of the microlab. Now that the conductivity probe has been plugged into the microlab, we need to open the microlab software. To do this, we simply click on the microlab icon on the desktop. You'll notice that it says reading from flash memory. This ensures that the microlab is properly connected to the computer. If you do not see this, it's probably because the microlab is off, the microlab is unplugged, or it's not properly connected to the computer by the USB cord. Check all of these things before consulting the TA for further assistance. Once the microlab software is opened, we need to double-click on Microlab Experiment. This will open a window which will allow us to collect data. In this case, we want to collect data about conductivity. To add the conductivity sensor, we click Add Sensor. Under Sensor Type, we select Conductivity. In the display that shows the front of the microlab, we must also click on the conductivity icon. In this case, we want to click 0 to 20,000 microsiemens because that's the range in which we want to work. We want to use factory calibration, so we simply click on Use Factory Calibration. You'll notice that this shows us a conductivity measurement in this window here. Once we have the conductivity probe attached to the microlab and the microlab software ready to make a measurement, we first want to clean the conductivity probe by swirling it in some deionized water. As you can see, there's a small conductivity reading as the probe is swirled in deionized water. Then simply use a paper towel to dry the conductivity probe as best you can. It's not essential that it's 100% dry. In order to measure the conductivity of the solution of interest, you want to have it in a 50 milliliter beaker, which is approximately half full of the solution. Then simply insert the conductivity probe into the solution. Once the probe has been inserted into the solution, swirl the probe for 15 or 20 seconds. Notice here that there is a relatively large conductivity. This is because salt is a strong electrolyte, and therefore the current is able to pass, and we measure that as a conductivity in microsiemens. As I swirl the probe, you'll notice that the reading stabilizes, not completely. Here you can see that in the tens place, the number is jumping around a little bit. Simply record a value that is approximately being displayed by the instrument. Here I would record 11,270. After making the conductivity measurement, it's important to clean the probe. To do that, simply insert the probe into a beaker of DI water and swirl it around. Then, wipe the probe dry with a paper towel. So now you've seen how to measure the conductivity of all of these solutions. And then when you're just going to want to do that one at a time, filling a small beaker about half full with each of these solutions and sticking in the conductivity probe. What you notice is as the concentration decreases, so too does the conductivity because less electrons can pass through because there are less ions in solution. So we have the concentration and conductivity of a 5, 4, 3, 2, and 1% solution. Note it's not exactly 5. And we have the conductivity of each of these solutions as well. We also take the unknown, which is our seawater solution, and we could find its conductivity, and the unknown concentration is going to be in mass percent. So we can also find the unknown concentration. So let's just look at these numbers. The unknown conductivity is 12,700 approximately. If we look here, a 3% gives us a response of 12,500, and a 4% gives us a response of 14,200. So you could see that the unknown is somewhere between 3 and 4%, because that's between these two values, and it's much closer to 3 than it is to 4, because it's much closer to 12,500 than it is to 14,200, 12,700 that is. So we know it's between 3 and 4%, closer to 3. A calibration curve will allow us to find this more accurately by finding the equation of the line. In order to do that, we need to make an XY scatter plot. To do that, what we want to do is select our data in the concentration, that's going to be our X, and our conductivity in the Y. In order to make this selection, I'm holding the control key and I'm highlighting the data, holding the control key the whole time. So I'm not holding the control key, I hold control, and then I select the data. If you're using a Mac, it's not the control key you want to use, but the command key. So you would want to use the command key instead of the control key in order to select multiple columns. So again, I highlight the first data, not holding the control or the command key. Then I hold the control or the command key down, and I highlight the second set of data. I now go to Insert and an XY scatter, like so. Now I have my data. I'm just going to shrink it down here so we can see everything. Now that I have my data, what I want to do next is I want to format my chart. In order to do that, I go to Quick Layout, okay, and I select, you can actually select this layout and it actually does the regression for you, or you can select this layout. I don't need this data point, so I'm going to delete it. On my x-axis, I have my concentration, and that's going to be in mass percent. On my y-axis, I have my conductivity. Whoops. Okay, I have the conductivity, and that's going to be in microsiemens per centimeter. Only one per centimeter. Okay, I didn't go as far as to put the micro key. You could do that. You could add a symbol, but I just went ahead and put microsiemens per centimeter. Now what I want to do is I want to add a linear regression. So I just click on any of the data points. I right click, I click on Add Trend Line, and it disappeared on me. So I'm going to do, there it is. All right, then I'm going to hit Display Equation on Chart and Display R Squared Value. Then I'm just going to come down here and I'm going to go ahead and make this a little bit bigger so that you can see it. Finally, I forgot to put a chart title, so I'm going to put that, and I'm going to put calibration curve of salt concentration versus conductivity. All right, so now I have a title for my graph. So now I have everything I need. One thing I want to note is that the R squared here is 0.9982. In this course, we say that the R squared should be 0.99 or better. So this is closer to 1 than 0.99, so this is better than 0.99. 1 is the ideal value for R squared. What this means is that the curve fits the data well. Said another way, all of these points are going through this curve is going through all of these points very well. If you notice here, if I change this to, let's say, 3,500, okay, now the R squared is very bad because now the line isn't going through all the points. So I want to just hit a Control Z on that so you can see now the curve fits the data well because the data is good. If your curve isn't good, you need to talk to the TA, but probably you need to remeasure one of these points. Hopefully you don't need to remake the solution. The other thing that this gives me is the equation of the line. I now have the equation of this line that relates y, conductivity, with x, concentration. I also have the conductivity of my unknown, which is a y value. So I simply want to solve for x. To do that, I type in equals, and the first thing I want to do is take this value, which is y, and subtract b, okay, the y-intercept. In this case, minus 8855, or excuse me, it's 8355.5. Then I want to take that value and divide by the slope, which is divided by 1424.5. I now have the unknown concentration, and the unknown concentration is 3.06. We've said it was going to be between 3 and 4, closer to 3, and mathematically we found it's between 3 and 4, closer to 3. So this is how we can analyze our data. Finally, we want to write a conclusion, which there is some information on page 53 to help us. Sentence 1 should contain the following: whether the results did or did not support the hypothesis. Well, we said in our hypothesis that it was going to be between 3 and 3.5%, whatever we Google and find out. So let's say it was 3%, and we found it was 3.06% salt in seawater. So we're good. What is the concentration of the seawater that was calculated? Well, we can use that from our Excel, and we found that it was 3.06%. What equation was used to find the seawater concentration? In this case, we used the equation of our line right here. We plugged in for y and we solved for x. Next, sentence 2 should contain the following. The r squared value for the line of best fit, which was 0.9982. This indicates that the curve fit the data well because it was 0.99 or better. Note that if it's way far away from 1, so if it's like 0.92, all right, then you're going to want to check your data, not simply write what's wrong with the r squared. All right, so make sure that you check in with the TA if your r squared isn't very close to 1, if it's not 0.99 or closer to 1. Sentence 3. The results indicate that the calibration curve is a good method for determining the concentration of an unknown because it's relatively easy to measure the conductivity. We stick in the conductivity probe, and the calibration curve can be used to determine the information we care about, in this case, the concentration of the solution. So I hope that you found this video helpful, and I do thank you for watching.